Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 6 on power functions and regression. So everything that we've learned lately with fractional exponents and other types of exponents, exponent properties, things like that, work our way up to a very simple type of function. Let's take a look at that right now. All right, power functions. Now that we have the concept of rational exponents, we can introduce a type of function with a very simple form known as a power function. Let's take a look. Power functions. A power function is any function that has the form f of x equals a times x to the b, where a and b are real numbers. All right, so you've seen power functions. Even something like y equals x is a power function. Y equals 7 times x squared is a power function, right? Any function that can be written in the form of y equals a number times a variable raised to another number is a power function. So let's jump into exercise 1 and take a look at a variety of different power functions and also evaluate them. Exercise number 1. Evaluate each power function shown below for the given input without using your calculator. All right, well, I bet letter A is pretty easy, so why don't you go ahead and do that one. All right, f of x equals 5 times x squared. Absolutely a power function. It's a number times x raised to a number. We want f of 3, simple enough, right? F of 3 is 5 times negative 3 squared. The great thing about power functions is because we simply have an exponent and a product, we do our exponent first. Negative 3 squared is 9, and 5 times 9 is 45. Every power function, in fact, right, you're going to be raising an input to an exponent, getting an answer, and then multiplying it by whatever that coefficient is. Let's take a look at letter B. G of x equals negative 4 times x to the negative 3. And we want to figure out what the value of g of 2 is. Okay, well, why don't you go ahead and try this one on your own? Okay, simple enough. So g of 2 is going to be negative 4 times 2 to the negative 3. The first thing that I want to do after substituting in my input is I want to figure out what 2 to the negative 3 is. That's going to be 1 over 2 to the third. So that's going to be negative 4 times 1/8. That's going to be negative 4/8. And that will simplify to negative 1/2. Okay. So this is probably the simplest of all types of power functions, a nice positive number times x raised to another positive number. Here it's a little bit more tricky, right, or a little bit trickier, where we've got our exponent that's a negative. And now let's take a look at letter C. We've got 5/2 times x to the 2/3, and we'd like to know the value of h of 8. A little hard for me to get that one out. Why don't, again, you pause the video and see if you can figure out the value of h of 8. All right, first things first, let's get that 8 into our function. So we've got 5/2 times 8 to the 2/3. Of course, you could do 2/3 on your calculator, but this problem says to try to do it without using your calculator. So I'm going to leave my 5/2 alone. 8 to the 2/3 is the cubed root of 8 squared. The cubed root of 8 is 2 squared. So that's going to be 5/2 times 4, which is going to be 20/2, and that is equal to 10. All right, excellent. So, all this does is to illustrate that power functions are very, very simple, right? They are a, if you will, two-operation function. The first operation is taking the input and raising it to a power, where that power could be a beautiful whole number, it could be a negative integer, it could be a fractional power. It could even be a negative fractional power. It could even be an irrational power, but we've mostly been sticking with rational exponents at this point. But there's no reason why it couldn't be like x to the pi, if you will. Anyhow, let's not complicate matters. Now, writing a function in power form. Sometimes power functions will not be written in their standard power function form. it's important to be able to write them this way. In other words, it's important to be able to write a function as a number times x raised to another number, if it's a power function. If it's not a power function, then we definitely don't want to write it that way because it would just be wrong. So let's take a look at exercise number 2. Each function shown below is a power function. Write it in the form f of x equals a times b to the x. Now, some of these are easier than others. Letter A is pretty easy. Let's do it together. We've got f of x equals 8 times the square root of x. Now, this is a power function because I've got 8 times x raised to the 1/2. And that's all this problem is asking me to do, right? I just want to phrase this as the following. 8 times x to the 1/2. Why you want it in that form is more questionable, all right? But there's many times, especially if you go on to study calculus, and many people who are in Algebra 2 will end up going on to study calculus either in high school or later on in college. It's very important to be able to take functions like this and write them like this. All right, so a little bit more challenging, letter B. Let's take a look. F of x equals 2 times the 5th root of x divided by 7. All right, well, I'd like you to pause the video now and remember, I want this written in a very specific way. I want you to write it as a number times x raised to an exponent. So pause the video now and see if you can do that. Well, first, keep in mind that I can think about this as f of x equals 2 times x to the 1/5 all divided by 7. Then I can think of that as 2/7 times x to the 1/5. And there is my power function form. All right, final one's pretty easy, I think. Take a look at letter C. I've got f of x equals 11 divided by x squared. Why don't you pause the video now and see if you can write that in its power function form. All right, well, keep in mind, I can think of letter C as f of x equals 11 times 1 over x squared, which means that can be thought of as 11 times x to the minus 2. And that is its power function form. All right, great. Again, little skills that we're doing here and there with power functions within this lesson, right? None of this is going to be radically new or different or crazy on you. We just want to kind of play around with power functions. So now let's talk about the y-intercepts of power functions. One of the most important features of a power function is its y-intercept. This will directly depend on the value of the exponent of the power function, all right? So the y-intercept is going to depend on what the power actually is, the exponent is in our power function. So let's take a look at exercise number 3. Each of the following power functions has a positive exponent. Determine the y-intercept of each without the use of your calculator. All right, so I just want you to evaluate the y-intercept of each one of these. Now, of course, the y-intercept, right? The y-intercept is the output when x is equal to 0. So pause the video now and just figure out what the y-intercept is of f of x equals 8x squared in letter A. Okay, well, simple enough, right? In letter A, the y-intercept is going to be f of 0. That's 8 times 0 squared. Of course, I have to do 0 squared first. 0 times 0 is 0. And 8 times 0 is 0. So the y-intercept of that power function is 0. All right, well, let's take a look at letter B. G of x equals -4 times x to the 10th. All right, well, why don't you go ahead and figure out what the y-intercept of that particular power function is. All right, well, let's take a look. In this particular problem, right, the y-intercept, again, will be g of 0, which is -4 times 0 to the 10th. 0 to the 10th is 0 times 0 times 0 times 0, etc., which is just 0. And negative 4 times 0 is 0. All right, well, whatever. Those are two, positive exponents that are whole numbers, so maybe that's not too surprising. How about the y-intercept of letter C? Why don't you pause the video now and think about that one? Okay, well, let's take a look. That's going to be h of 0, which is 6 times 0 to the 1/2, which is 6 times the square root of 0. Now, before we go on, right, let's talk about the square root of 0. Right? The square root of 0 is that the number, when it multiplied by itself, gives me 0. A lot of students, for whatever reason, think that the square root of 0 is undefined. Well, no. 0 times 0 is 0. So the square root of 0 is 0. Side note, the cubed root of 0 is also 0. And the fourth root of 0 is also 0, right? Because if I raise 0 to any whole number, integer power, right, any positive integer power, I get 0. So the equivalent root of 0 is also 0. Man, I said 0 just a bunch, right? That's going to be 6 times 0, and that's 0. Well, that might have been the easiest exercise that we've done in Algebra 2. The answer to A, B, and C is 0. And that leads us to exercise number 4. What can you say about the y-intercept of any power function whose exponent is positive? What point then must every power function of this type contain? All right, well, pause the video right now and see if you can answer those two questions. All right, well, the y-intercept, question 1, if you will, the y-intercept will be equal to 0. And 2, that means the point 0, 0 must be on its graph. All right. Now, again, I want to really emphasize, this is for power functions where the exponent is a positive number. Where the exponent is a positive number. So when the exponent is a positive number, taking 0 and raising it to that positive number gives me 0. And then multiplying it by that, whatever that constant is, and it doesn't matter what the constant is, I still get 0. So every power function with a positive exponent has a y-intercept of 0, which means the origin, the point 0 and 0, lies on every power function where the exponent is positive, which is kind of cool, right? That's not true of a lot of different functions. Now let's talk about power functions with negative powers. We will be far less concerned with power functions that have negative exponents for now. But it is instructive to briefly look at their y-intercepts. So let's take a look at exercise number 5. Rewrite each of the following power functions so that they do not contain negative exponents. Then evaluate their y-intercept if possible. All right, great. Well, why don't you go ahead and try that for letter A and see what you find. If you absolutely need to, use your calculator, but I'm hoping you don't need to. All right, so here we have f of x equals 10 times x to the negative first power, to the negative 1. I can rewrite that without negative exponents as 10 divided by x. So now, if I want to try to find my y-intercept, I do something like this, and I find that f of 0 is 10 divided by 0. But division by 0 is undefined. Undefined, so the y-intercept does not exist in letter A. All right, just doesn't exist in letter A. All right, why don't you try letter B? Okay, same song, second verse, right? I have g of x equals 1/3 times x to the negative 4th. I can rewrite that to the negative 4, as 1 over 3x to the 4th. So if I want g of 0, that's going to be 1 over 3 times 0 to the 4th. That's going to be 1 over 3 times 0. That's going to be 1 over 0. And yet again, that's undefined, so the y-intercept does not exist. Never touches the y-axis. And finally, letter C. h of x equals 8 times x to the negative 1/2. Why don't you go ahead and try to figure out what the y-intercept, if it exists, is of that particular function. Okay, so we can rewrite this as 8 divided by x to the 1/2. Then if I want to think about that in terms of roots, I can rewrite that as 8 divided by the square root of x. So h of 0 is 8 divided by the square root of 0, which is 8 divided by 0, and that doesn't exist. So the y-intercept does not exist. So we're kind of beating the same drum here, right? If I've got a y-intercept, or if I've got a power function whose exponent is negative, looks like the y-intercept doesn't exist. So that is truly the answer to exercise 6, but let's take a look at it. What can you say about y-intercepts of power functions that have exponents less than 0? Well, we can say that they don't exist. Oops. They don't exist, and make that actually look like an S. And it's kind of cool, right? Because ultimately, if you look at a power function, f of x equals a times x to the b, if you look at that, right, it basically boils down to this, right? I've got x raised to an exponent. If that exponent is positive, then I'm really thinking about multiplying. So if x is 0 and I'm multiplying by 0, right, then I'm going to get 0. But if that exponent is negative, then I'm going to be dividing. And if I divide by 0, then I get something that's non-existent. So in terms of power functions, right, they really break down into two very distinct categories. In one category, the exponent is positive, and the function passes through the origin. In the other category, the exponent is negative, and the function never even touches the y-axis. All right, let's keep going. Now there's one last thing that we're going to look at today, and that's what's known as power regression. Power functions with positive exponents are extremely useful in fitting bivariate data sets where the two variables are 0 at the same time. Now before I go on and kind of go through the rest of this, right, positive exponents, right, what we just talked about is if I have a power function that has a positive exponent, it's got to pass through the point 0, 0. So if I've got some kind of bivariate data set where the two variables are 0 at the same time, then it makes sense to try to fit it with a power function because power functions with positive exponents always contain that point. Now the regression is done in the same manner as what we have seen before, okay? So the actual procedure is identical to what we saw with linear regression, exponential regression, and quadratic regression, right? All three of those we did exactly in the same way. We entered the data in the same way. We just had to hit the right button on our calculator. Let's take a look at exercise number 7. May was measuring the height of germinating corn plants as a function of the days since they first broke the soil for her 8th grade science fair project. She measured the following data. All right, so, right, our input are the number of days since the plant first broke the soil. And it kind of makes sense, right? Day 0, the plant height is going to be 0, right? Day 0, the first day that they kind of like break the soil, they're right at the soil surface, right? The plant height is at 0. So it kind of makes sense why we might use a power function here. Now after 2 days, right, the average plant height is 6.3 centimeters, 5 days, 9.1 centimeters, etc. Let's take a look at letter A. Use your calculator to find an equation in the form y equals a times x to the b that best models this data set. Round both constants to the nearest hundredth. Okay, great. Well, let's kind of review how we do this. Now, for myself, right, I've taken my calculator and I've actually already put my data in here. I just have to open up the document. All right, and that's going to be this one. All right, so I've already in my TI Inspire put my data into a spreadsheet. Now I've labeled the x column as time and I've labeled the y column as height. And my usual cautionary tale is there. Make sure that when you enter this data, you look over it multiple times, okay? Because if you're doing this, let's say, on a very high-pressured state exam, right, and you put a single one of these numbers in incorrectly, then the regression equation that you get out at the end is going to be incorrect. All right, but I checked these over repeatedly, so we should be good to go. Now what I'm going to do is I'm going to hit Menu, right? I'm going to go to option 4, which is Statistics, okay? And then I want Stat Calculations, so I'm going to do that. And then I've got all of these different types of regression, like my linear regression in choice 3, like my quadratic regression in choice 6, like my exponential regression in letter A, right? My power regression on the TI-Nspire is down here as choice 9, power regression. In terms of my X list, I'm going to go over and I'm going to choose time. In terms of my Y list, I'm going to choose height. I'm not going to worry about anything else. I don't need to futz around with any of these things. That's more kind of like advanced stat, and I hit enter. Now what I see is I see the form of the regression equation, a times x raised to the b. Then they immediately give me the value of a, 4.314, etc. The value of b, 0.489, etc. I just have to kind of worry about what it wants me to round to, and I want to round both constants to the nearest hundredth. So for me, that is going to be y equals 4.34 times x to the 0.49. And again, you can see why if I even am a little bit off on any of these things, then I've got a problem, right? Because I'm going to end up having one of these two constants incorrect. And let me just put that decimal point a little bit bigger so that those of you watching this on a very small screen can see it. All right, and a beautiful power function, right? Some number times x raised to some number. It's in fact a power function where the exponent is positive, okay? And that sort of makes sense. Let's take a look at letter B. Use your model in part A to interpolate the height of the corn on the 30th day. Round your height to the nearest tenth of a centimeter. Awesome. Well, this is pure, straight up calculator work. See what you get when you do that interpolation to find the height of the corn on the 30th day using the model. Okay, well, it really is calculator work. We're just going to like show the substitution. I'll have y equals 4.34, make that look like a decimal, times 30 to the 0.49. We're going to like literally just put that in our calculator just like that, and we get 23 centimeters. All right, by the way, it's kind of cool because you can sort of like look, right, that 30 falls between the 25 and the 35, right, and that 23 falls between the 20.6 and the 24.7, so I'm feeling pretty good about that. And again, it's called interpolation because we're using our model to predict an output where the input falls within the range 2 to 42. All right, let's now do a little extrapolation. Let's take a look at letter C. Use your model from part A to extrapolate the height of the corn at the end of the 60th day. Round your height to the nearest tenth of a centimeter. All right, well, why don't you go ahead and use your model now to extrapolate the height of the corn at the end of the 60th day. All right, here we go. Well, again, we're just sort of using our model. We've got y is equal to 4.34 times 60 to the 0.49. And when we crank through that, we get 32.3 centimeters. You know, I just realized in that previous one, I rounded it to the nearest centimeter, and it says to the nearest tenth of a centimeter. Let's take a look really quickly at whether or not that's correct, just to make sure. Let me come over here. Let's go in here. Let's just take a look at 4.34 times 30 raised to the 0.49. And that's 22.976, right? 22.976. So technically, if this is really to the nearest tenth of a centimeter, technically I should really have 23.0 centimeters, showing to the nearest tenth that actually rounds to 23.0. My apologies for that error. All right, let me kind of go back into this. Now again, just as a side note, right, 60 days, right, is outside of this interval of our input. It's, somewhere out here. And of course, then we're predicting a value of 32.3. Again, let's get that decimal place a little bit bigger, which I feel pretty comfortable with given that that's bigger than our 27.6. All right, let's look at one final issue with this. Letter D. For simplicity, May concluded that the average plant height can be modeled with an equation of the form y equals a times the square root of x. Is she justified? Explain. All right, well, let me write down the model so that we have it just sitting here. Y equals 4.34x to the 0.49. A lot of times in math, we do want to kind of simplify models so that we can think about them a little bit easier. Would May be justified in simplifying her model into the form y equals a times the square root of x? Pause the video now and think about that a bit. All right, well, I would say yes. Now again, this is a little bit of a discussion, right? I would say yes, because the square root of x is x to the 0.5, and May's exponent of 0.49 is very close to 0.5. Now, I could see somebody making the argument that, well, the square root of x is x to the 0.5, and May's exponent is 0.49, so those two are too far apart for us to simplify it as the square root of x. But you'd have to make that argument. Now, how close is close enough? If it was x to the 0.41, would that be close enough to say square root of x? I would say no, right? But x to the 0.49 is quite close to x to the 0.5, which is the same as the square root of x. So I'm going with yes on that, because again, it would be nice to kind of have the equation in this beautifully kind of more simple form. 4.34 times the square root of x. We're more comfortable with, let's say, the square root of x than x to the 0.49. All right, let's wrap this up. Power functions are some of the simplest functions out there. They combine a product with a variable raised to an exponent. That's it. There's no additive constants, there's no additional x's in the function, nothing like that. And they really range the gambit from things like lines, y equals mx, no plus b, just y equals mx, that's a power function, to simple quadratics like y equals 10 times x squared, that's a power function, to y equals the square root of x, that's a power function, right? All those things are power functions because power functions are monomials that take the form of a number times x raised to another number. Now, we just explored them a little bit today, including looking at how their y-intercepts are directly dependent on whether or not the exponent is a positive number, in which case their y-intercepts are just at the origin, or are a negative number, in which case they don't have a y-intercept whatsoever. Finally, we looked briefly at how you can do power regression, i.e. fitting a bivariate data set with a power function, and that is only going to make sense if the physical context means that both the input and the output, the x and the y variables, would be 0 at the same time. All right, well, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.